Okay, hi everyone. Thank you for joining our 2023 SEDS projects presentation. Today we're lucky to have two teams of university students that will be presenting on their experience at this past year's flight campaigns and the results they got from their respective experiments. The first team presenting will be Stratospheric from the University of British Columbia, Okanagan, who participated in the Canadian Stratospheric Balloon Experiment Design Challenge, short-formed CAN-SBX, just this past August, where they launched their science experiment on a high-altitude balloon provided by the CSA. Next, we'll have Mission Spacewalker from the University of Alberta that participated in the Canadian Reduced Gravity Experiment Design Challenge, short-formed CAN-RGX, just this past February, where students got to fly with their science experiments in microgravity aboard one of the National Research Council's Falcon 20 planes that was specifically modified to work with reduced gravity by the Canadian Space Agency. So I'll pass it off to Abrar, the team lead for Stratospheric, to kick us off.
Thank you very much. I'm just going to start sharing my screen for the presentation I have prepared. Okay. So I would like to start with thanking everyone here for this opportunity. I believe it will have a lot of good impact on sharing our information and sharing our experiences and build a way for the next future teams. So I'll be going over the introduction, some of our goals, some of our designs, and the results we got, some of the adaptations, what's our next steps, some of the outreach problems we have, and outreach potential we have, and also some of our challenges. So to first of all start with what is single event upsets? It's the main topic that our project is focused on. So we have two phenomena that occurred in 2008, where a Qantas Airbus plunged twice mid-flight in quick succession. On the other hand, we have an election in Belgium in 2003, where a candidate voted 4,096 extra votes. That brings to the question: what is a common event, or what common factor is between these two events? That's when we have to answer single event upsets. So singular upsets are caused by the hordes of invisible particles from outer space, some from the solar system, some from out of our solar system, that results in election being data corrupted, being planes plummeting from the sky, and also smartphones freezing and whatnot. So these originate from cosmic rays from outside of our solar system, and these tiny particles constantly bombard the Earth, with millions hitting each human on the planet every day. And one of the phenomena that these have is on data, which is on SSDs originally, and they can cause a bit to flip, which is from 0 to 1 or from 1 to 0. So galactic cosmic rays, solar particles, and radiation belt particles collide with these atoms in the upper atmosphere to create showers of subatomic particles. These can cause a neutron flux and can cause bit flips, or as we professionally call it, single event upsets. So observing these phenomena, we as a team thought there's a potential for an experiment where we will investigate how different cell architectures can help to mitigate single event upsets in different types of SSDs. So our previous team captain, Yosemite Hassanullah, formed a team of 8 engineers, including me, who came up with an experiment idea that could greatly utilize this opportunity and the opportunity provided by SEDS and CSA. Our experiment was very simple initially. It was just a Raspberry Pi connected with 4 SSDs of 2 terabytes of binary data, and they were sent up, and two of the SSDs were planar and 2 of them were 3D. I was responsible for designing the mechanical aspect of this project, and I had the chance to go to the Montreal Bay, CSA base in Montreal, and also visit the Timmins base, where we had our first flight with our relatively simple project. Second year, which is UBC Stratospheric Generation 1 and 2, was our, after our first successful flight, I had the privilege and the honor to take over as team captain with the intention to further upgrade our experiment. So with a lot of help, and to people that I'm really thankful for, including Radu David, Shia Saxena, Tariq Al-Gabbani, and Joao Lopez Bandy, The experiment setup was upgraded with 5 SSDs of 2 terabytes of binary data, and it also had an improved host computer, a Geiger counter that I will go over and explain further later on in this presentation. So our goals for last year. Number one was compare and contrast the number of single event upsets occurring in the 2 different types of SSDs. Second was comparing the total amount of single event upsets relative to the time in the stratosphere with the expected amount from the model data in published research. The third one was comparing the bit flip timing with the timing of the radiation spikes from Geiger counter. This would eventually help us to validate that the single event upsets caused due to radiation, due to a bit flip, due to a single event upset, and not due to some error in computer code. So our payload design. Our payload design was mainly made out of external foam structure, which was tested and vacuum tested, temperature tested, and it was good for us. It was cheap, it was readily available. Second was it was press fit mounting design. We had basically tabs on our custom interface plate, and that helped us reduce the assembly time much easier. There was not a lot of fasteners going through our foam structure. And our structure was mechanically sound, and it survived both times with very good results, no crack or no defects at all. So which was mechanically, our structure was quite good. Our electrical setup involved of a host computer, which was powered by a battery, and it was connected to 5 SSDs, and it was one with our custom operating system and a Geiger counter run by the host computer. So our experiment results. Our host computer logged data for 1 hour into the stratospheric flight. However, and then rather unfortunately, it stopped functioning after 1 hour of ascent. So this raised some concerns, and we had to run into some analysis afterwards of why this happened. So after post-flight trial runs, it was evident that the computer overheated at ambient temperature during the flight, and the thermal system, safety system that we had installed caused the computer to shut down. So there was kind of a, in hindsight, what happened was we tested our computer to survive the cold temperatures on its flight, which is about -6 degrees, and we tested our computer to -80 degrees. It was running fine at those sub-zero temperatures. However, on that day of the flight, it was very sunny, and there was a lot of time in that ascent of the payload where the computer overheated over time and caused it to shut down. The Geiger counter, on the other hand, recorded data for 2 hours into the flight, and the radiation exposure recorded that it was sufficient for bit flips to occur. However, the host computer shut down before it was reached enough height for radiation to occur. However, there was another concern of why the Geiger counter would stop recording data 2 hours after the flight and not after the flight was ended. Analysis showed that the glass tube of the Geiger counter shut down and broke due to the combination of pressure drop, low temperatures, and payload vibrations. The payload structural performance was satisfactory. This foam was intact, and all the electronic mountings were quite as per expectation. In addition, the assembly process was also easy and time efficient. So our successes were our battery, we survived enough power, and it served its purpose. It was absolutely spot on. Host computer, performance-wise, in terms of SSD reading and everything, was quite good, except it overheated, which is the thermal management problem. Structural integrity, as I said, and very easy integration. Our failures, computer overheated, as I said. The Geiger counter, as I said, broke, and our alternatives are now having a separate mounting system for the Geiger counter, or investigating into a more expensive Geiger counter with better shielding. And another thing that's not as catastrophic failure as the other ones is internal wiring, which was for its compact design was very not as organized as we wanted to. So that's an improvement we will look into this year. So fighting our overheating problem. So some of the potentials we look into is having it retested at -8 degrees Celsius, confirming that it runs at that temperature. Next is having a heat sink. That's the most simple one and probably the one that we will go for, which will have like a heat sink connected to the external atmosphere, and the computer should be running at those cooling mechanisms. Second is host computer climate active climate control, which is a bit more complex, but something we are kind of looking into. But if the heatsink process works, we will not be going down that path. Another one that we will have either way is the electrical relay system, which will try to activate the host computer at intervals so that even if it shuts down due to high temperatures or overheating, it can be turned on when it reaches those cold temperatures of the stratosphere. Like I said, some of the remedies for lesson learned is testing more into the thermal protection of the host computer, and some of the factors of risk of transportation and improve wiring, investigate more into finding better solutions for Geiger counter, better focus on academic outreach, and separate dampening system for the Geiger counter. And we are also looking into buying a Geiger counter that might be or renting a Geiger counter that might be way above our budget. And that's why we're looking into collaboration with a laboratory that might let us borrow their Geiger counter, but that's still in the works. We also have a better risk analysis in set up for this project because we had an Engineer 303 project management course project just based on our Saturn years project. I would also like to share and thank CSA and SEDS for the price list opportunity that they have provided for the team. Our team had a lot of experience in engineering design, in project management, in research development, the whole process of experiment design. Some of the manufacturing that we did in-house, also public outreach, some of the professional network that we have built across UBC, CSA, and also industry partners, and obviously for our project risk analysis and cost analysis. I would also like to take this opportunity to share one of the most difficult situations we have faced last year in Kelowna, which was Kelowna had a really bad season of forest fires. The McDougall Creek wildfire tore through our central Okanagan 3 days before our flight. As you can see, some of the pictures just 2 days before flight, and the picture on the top bottom right just shows the scene in Kelowna as we were heading towards Vancouver. Our flights were getting canceled. We had to drive to another airport and then take consecutive flights to reach Timmins. We are very thankful that we were able to reach Timmins and proceed with our project. However, this does pull attention, like the climate changes that are happening in this world is very evident. Global warming is no longer just a theory we read in books or something we read in our textbooks. It's starting to impact all of us, and it calls to action for all engineers and professionals and professionals and also students and the next generation to be more conscious, to be more aware about this. I would like to share some of the pictures that we have gathered over the last years. It's at the Timmins base. This is before installing, during our flight, and just as the flight ascent started. So I would like to share some of our outreach. We had our names, our projects shared across UBC Okanagan News, Sky News, Space QNet, and also we had the opportunity to share our project to IEEE events on campus, which greatly helped us to contact industry partners. And yeah, and then as for the last part, I would like to share some of our funding information. We are very thankful to UBCO Professional Activities Fund, which accounts for 60% of our budget. We also got significant funding from 2MEST, which accounted for 20% of our project. And we'd also like to thank UBC Integrated Optical Laboratory under Professor Jonathan Holzman, who has helped us greatly in purchasing and the materials for the manufacturing process. Thank you very much.
Thank you so much, Abrar, for the fantastic presentation. I'll leave, if anyone has any questions, a moment now for you to put it in the YouTube live stream chat, and we'll address them as they come in. while we wait for that, I was hoping I could ask one of my questions to you about how CAN-SBX works. So you launch this balloon with your payload on it up into the stratosphere. Can you control where it lands? And if not, how do you know where it lands? How do you retrieve it? How does that whole side of things work?
So unfortunately, we cannot control where it lands. However, there's a funny story to that. 2 years ago, during our flight, we had an accident where the payload reached a gold mine, and that was a huge concern. However, it was recovered safely. So even though we cannot determine where it lands, we do have a tracking process involved that that shows us where it landed. And thankfully, even though there has been cases before um, that their payloads were lost completely, two of our flights we did recover the payloads, so that's good news for us.
That's awesome. I didn't know about the gold mine incident. That's quite interesting. We
Yeah.
got one that rolled in from the YouTube chat. I'll pose it to you. Beautiful presentation, they say. Have other teams encountered overheating, and do they mainly use the heat sink solution, or was it also just particularly hot this summer?
So I am not entirely sure if other teams face overheating. They do certainly face overcooling. Our computer running at those speeds and the bare backbone of it did not face overcooling. It did face overheating. Um, I am not entirely sure what solution they use. I do know one team which used active climate control, but that was like a more professional team than us, and they obviously had more experiences, so something to learn from. Also, it was I do believe, at least from my last two experiences, it was particularly hot this summer on the flight day.
Cool, that makes a lot of sense. I guess a follow-up question, what do you mean that they were more professionally experienced than you? Like they're not students?
No, they were not students. So we are a student team, student run and everything. I believe that was one of the teams who were 2 years ago, who were from one of the university research groups, and they shared that they did use active climate control.
Cool. That's super interesting. Okay, one more question for you. You showed that you were able to go to the Canadian Space Agency headquarters. How was that? What brought you there? And how did you enjoy it?
So I had the chance to go there 2 years ago. It was our first flight, and our team was more concerned about whether we can integrate it properly. We were so much in the unknown. We did not have the experience. We were just a newborn team, and it helped us greatly to like confirm that our project is going the path we wanted. Apart from that, we got to see the Canada arm model at CSA and had a small tour around the premise, and it was amazing. I know it might sound disrespectful to the project that we are doing, which is obviously a lot of research, but that's definitely one of my top experiences to be able to see that CSA headquarters.
That's great to hear. No hard feelings. It does sound like a pretty unique experience. Okay, well, I'll wrap things up here and we can come back to both of the teams together for a longer question period if we have time at the end. I'm going to toss it over to the mission spacewalker leads.
Thanks, Ashley. Well, welcome to the Mission Spacewalker post-flight presentation. I'm McKenna, and I'm joined by my co-president, Jana, and we're going to talk about our experience with our CAN-RGX project. So a little bit of background, Mission Spacewalker is primarily an undergraduate student group, and we're focused on space exploration and providing different opportunities for women and gender minorities. So we were founded in response to the Canadian Reduced Gravity Experiment Challenge, or CAN-RGX, hosted by SEDS, and our project focused on electroadhesive climbing robotics in microgravity. Also, currently, this was our project we did last year, and currently right now we are participating in the first Canadian Analog Research Expedition, or CAN-RGX, also hosted by SEDS. So our mission statement for this project was the investigation of effectiveness of electroadhesive robotics in reduced gravity, on various materials and validating the testing procedure. So that's a little bit of a mouthful, but basically what we wanted to do was test electroadhesive robotics in microgravity. The vision was on the International Space Station, we have robotics like the Canadarm, but it has to be attached to the space station. What we envisioned was robots that didn't have to be tethered. They could roam around freely on the outside of, say, the International Space Station or a meteoroid, collecting samples, or surveying the station to make sure everything was working properly. And our solution to that was electroadhesion. So why electroadhesion? Well, one special thing about electroadhesion is that it makes the wheels sticky. So it does this by polarization. We have two electrodes that are oppositely charged, and we create a static attraction force. This is similar to if you rub a balloon on your hair and it sticks. You have the balloon with one charge and your hair with another, and that creates that attractive force. We're doing this through high voltage, so the positive and other charged electrode create that field around the substrate that they're on, allowing it to stick. Typically, high voltage is quite dangerous, but we were using a very low to the microamp current. We still ensured we had all of the safety procedures required for high voltage, but it's not as big of a risk when we say high voltage for electroadhesion. So our outline for this presentation is to go over a bit of our mission objectives. We're going to go over the design review, also testing that occurred for the electroadhesive pads, then onto the flight campaign and our research from the flight tests, and then onto our outreach. So our mission objectives were to first implement an automated, fully enclosed testing setup. We did this in a Pelican case to study our robotics and microgravity. We also wanted to characterize the behavior of the robot in microgravity. We did this with a variety of different sensors, which we'll get into. And then we wanted to see how the electroadhesive pads on the wheels engaged with different surfaces. So onto our design overview. We'll start with the structure. So our structure fit inside the Pelican case. You'll see it here. It's a two-tiered design because we wanted both conductive and non-conductive substrate. So we actually had two robots, one on the top and one on the bottom. And then you'll see the camera placement here. Those helped us get a close-up shot and a wider shot of the robot. So we actually had 6 cameras in total. So we made this out of wood. We wanted to make sure it withstood a load of 2 times its mass. We did this by static load testing, including placing textbooks on top of the frame and making sure that it could withstand those forces. We made it through using a bandsaw and a CO2 laser cutter to cut all the pieces, including the acrylic that was on the bottom and the aluminum that was on the top. And then it was all together with fasteners, and it fit inside a Pelican case, which you can see on the right here. So some key features is it was completely enclosed. It's important to note that we kept it inside a Pelican case. And this is important because when you're in microgravity, things can fly everywhere. So we wanted to make sure it was contained. And this is a requirement for all CAN-RGX teams. We also had 2 tiers. So we had the acrylic on the bottom, which is our non-conductive substrate, and then aluminum on the top. And then we had guide rails. This is also important, and it goes back to in microgravity, everything flying everywhere. We wanted to make sure the robots couldn't move uncontrollably and also reset. So we had a guide rail, which the robot moved back and forth, and there's actually a gap in the claw to make sure the claw is the top connection piece on the rail to make sure that in microgravity, it doesn't actually have an effect, but it makes sure that, say, it wants to fly out or we hit a bump, it doesn't flip over, for example. So onto our robotic system. Some key features to note are we had a sliding lid. This was important because our electronics and sensors, all of that went in the center of our robot, and we wanted to make sure it was accessible for prototyping and testing. We had an ultrasonic sensor, which kind of looks like the eyes of the robot. But for those that know how an ultrasonic sensor works, the signals are sent from the sensor itself, bouncing off whatever material it comes in contact with, and returns to the sensor, and it can calculate the distance. So we use that to determine the position of the robot. We had tracks, or the wheels, which were commercial off the shelf, and we attached the electroadhesive pads to these wheels, which you will see in later slides. And then the guide rail, which is kind of that claw right behind the ultrasonic sensor. And for our electronics, so we designed everything around Arduino. Arduino is what our sensors connected with, and also the signals that were sent to the computer came from our Arduino. We had limit switches. So for those that have like Roomba robots, it's similar where if it hits a surface, it sends a signal to our Arduino to go the other way. So that made sure the robot could go back and forth without us having to tell it how to do so. We could pre-program that. We had an accelerometer to record the position as well as the acceleration. So when we were in hypergravity and microgravity, and then our ultrasonic sensor to record the linear movement. And all of our data was sent through CoolTerm software, which basically just turned the output from our Arduino into a text file that we could analyze after the campaign. I'll hand it off to Jana for our electroadhesive pads.
Awesome. Hello, everyone. My name is Jana, and I am one of the co-project leads for Mission Spacewalker, as well as during the campaign of the CAN-RGX 5, in which we participated in. Jumping right into the electroadhesive pads. So the electroadhesive pads, as you may have gathered, were one of the major components that went into our experiment itself, and a lot of our research focused on this specific area. Jumping right into the design of the electrodes, as McKenna mentioned, the electrodes themselves are what generates that static attraction to the different substrates in the project or in the experiment. And so for our electrode design, we decided to go with an interdigitated design. So there are plenty of different ways that you can design an electroadhesive pads. This involves two electrodes that are parallel to each other in more of a linear strip. This could also involve a single electrode in which your grounded electrode is actually the material you're testing on. For us specifically, we adopted an interlocking design. This can be thought of to be similar to two combs in which their teeth fit inside each other perfectly. And we adopted this because both with our own collected preliminary design data, as well as a literature review, this showed that it had the highest shear force generation, which was super important for the experiment at hand. So our electrode design was manufactured out of 15 micrometer thick aluminum. And this was kind of sandwiched between two sheets of polyurethane, which acted as our dielectric. So for our manufacturing method, just digging a little bit deeper into it, it can be simplified into two major steps. And our main goal with our manufacturing method was to ensure that it was both low cost, but also easily replicated by others who may be interested in exploring electroadhesion on their own. So for our design, it's first starts off with the cutting of the electrode design, which for simplicity, we utilized a fabric cutter, which was super important to enable us to get that interdigitated design and allow for us to ensure accurate and precise spacing between the electrodes. From there, we transferred it to our dielectric material. And there are a number of different ways that you can do this. For us, we use double-sided tape to accurately pick up the electrodes and transfer them over to our dielectric. Once placed on our dielectric material, we were able to remove that double-sided tape and place the other sheet and then kind of sandwich the electrode there. And then that led us into our step 2, which was actually heat pressing the materials together. The use of a heat press allowed us to minimize the air bubbles as well as ensure good lamination between the different materials. To actually power our electroadhesive pads, we utilized a high voltage layout, which you can see here on the screen. There were 3 main pieces of of hardware that were utilized. This included a regulator, 200 mega ohm resistors, as well as a high voltage converter. And essentially how this worked is we utilized the power supply from the outlet that is installed on the Falcon 20 plane, which gave us 5 volts, and that regulator essentially allowed us to implement a 1.2 volt drop, bringing us down to a 3.8 voltage. From there, we were able to take that through to our high voltage converter, which converted that from 3.8 volts to around 7.5 kilovolts. From there, we had a simple board that consisted of our 3 resistors. We had 2 in series, and these seried resistors were in parallel to our supply, and they just acted to limit the maximum voltage that our electroadhesive pads actually experienced. And then we had 1 in series with the output, and this was just to prevent any shorting that could occur during the experiment, ensuring both the safety of the equipment, but also the safety of our mission specialists during the flight. So for our testing methods, we performed ground testing before the flight. This included the quantification of both the shear force and the normal force. For our shear force setup, we utilized an applied mass on a tabletop that was attached to our pad. And essentially what we were looking for was a limiting force. And we would observe that limiting force or that maximum force once we observed qualitatively a shift in the pad. For our normal force quantification, we used a more counterweight method where we placed the substrate material over top of the pad. And with the increasing mass, we would wait to observe the lifting of the substrate material off of the pad itself. So our ground testing procedure, utilizing those 2 methods, was essentially broken down into 3 rounds. Round 1 was our functionality testing, which allowed us to qualitatively test for adhesion and observe actual attachment to the different substrates that we plan to test in microgravity. For our second round, we were looking to quantify that limiting force, and that occurred in 3 separate tests during this round to look at the normal forces generated on the paperboard, as well as the 2 substrates that we're looking at as a more of a control. And then for round 3, we were looking to do longevity testing. So we were hoping to explore a successful application of the 7.5 kilovolts on the electroadhesive pads for at minimum 20 minutes to replicate what we would actually observe during the flight. And here we were looking for signs of just minimal degradation of the pad itself. So we alternated here between round 3 and round 2 to just see if there was a decrease between that normal force that was generated. So some of our results from the ground test itself can be seen here. We approached these results in a more iterative manner, where we observed electrode breakage. We ensured to alter those measurements, including the electrode width, electrode spacing, the pad length, and the pad width. And from there, we're able to condense down to a few optimal designs, as can be seen here with our maximum shear force that we were observing.
So onto our flight campaign. Our flight campaign took place in the SAIT Aerospace Center in Calgary, Alberta. In this video, you can see us experiencing microgravity for one of the first times, me and my mission specialist, Jennifer. It is quite fun, and also you can see on the dials how the trajectory of the plane changes and also the gravity. So our mission plan, first, to talk a little bit about how a parabolic flight works. It's explained really well in this diagram to the right. First, we start off with a level flight, or 1G portion. This is similar to what we're feeling right now, or when you're flying in a plane in the sky. Typically, level flight 1G feels pretty more normal, and then we'll hit hypergravity. So this is a pull-up when we start that parabolic flight trajectory. It lasts for about 20 seconds, and then we get to kind of the crest of the parabola where we experience microgravity. So this is when we do our data collection and our motors are on. They're hopefully moving the robot back and forth, and then it should be noted that our electroadhesive pads are on for the whole duration. And then when we get to the end of that weightlessness portion, or the microgravity, our motors shut off to hopefully not move our robot anymore. And then we get into the recovery phase, where we experience another hypergravity portion of about 2G. And then you get to either another level flight, or you can pull up and do consecutive parabolas. Around 5 to 8 parabolas was what we were doing, and then we went into level flight to turn the aircraft around. But level flight can also be used for, say your experiment goes wrong and you need to open the Pelican case to fix something. Level flight is also good for that. And we did about 31 parabolas. And for the purposes of talking about our results, we analyzed the first 2 flights. So our shakedown, which is just making sure everything works properly, and then our first data collection flight, which Jana will talk a little bit more about.
So moving right into our flight results, it's important to note that during our flight, we unfortunately did experience some motor failure, which made us unable to observe any linear back and forth motion of a robot, which made it quite difficult to analyze for our objectives. However, we were able to observe wheel rotation both clockwise and counterclockwise, allowing us for some room to quantitatively analyze our results. So I'll jump right into our flight. For flight 1, we were able to test across a total of 12 parabolas. And for our quantitative observations during our microgravity, during the microgravity portions of the flight, we were able to see plus or minus 2 centimeter differential as observed by our ultrasonic sensor. And this is inconclusive whether that is due to actual movement of the robot on the substrate itself, or just due to the plane and the shifting on the guide rail of the robot. However, we were able to qualitatively analyze our 2 video feeds. So for our first flight, there was confirmed evidence of, or there is confirmed evidence of engagement on the aluminum substrate, indicating polarization of the pad to the substrate itself during those portions. As well as evidence of acrylic substrate disengagement, which can actually be seen here in the video. You can see the tread of the robot lift off of the substrate itself, indicating that the pad itself is not actually sticking and instead floating during those portions. Moving on to flight 2, we also had a total of 12 parabolas. And for our quantitative observations, we were able to observe a plus or minus 1 centimeter differential through the first half of the parabola, so the first 6. Whether this indicates engagement of the tread on the substrates themselves is inconclusive, and this was observed qualitatively. So there were inconclusive evidence of whether the engagement of the whether there was engagement of the aluminum substrate with the pad itself. However, there was evidence of slipping of the acrylic due to disengagement, and this agreed with the pre-flight ground test results that we saw. As a quick overview of our results, unfortunately, due to the motor failure that we experienced, we have inconclusive quantitative results on the engagement of the pad and the linear motion of the robot back and forth during flight. However, we do have evidence of limited normal force generated on the acrylic substrate as expected. We have inconclusive evidence of limited or minimum normal force generated on an aluminum substrate. And then we have inconclusive evidence on any shear force generated due to the motor failure as well. Going over some of our learnings of the flight itself, I'll talk a little bit about what worked and what didn't. So in terms of what worked, our structure, starting off with our structure, the data collected within our structure design allow for both quantitative and qualitative collecting. or collection, both through the sensors and the camera footage, as well as the rail, in fact, did work to prevent any uncontrolled motion during the microgravity portions of the flight. And this could look like any floating or just complete disengagement of the robot within the Pelican case. In terms of our procedure, there was no needed human interaction during the flight, which allowed us to keep it fully enclosed and have a fully automated system. And for our electronics, our cameras were able to obtain visual data of the experiment, both on the wider range as well as close-up. The ultrasonic sensor did record the position as expected, as well as our accelerometer data did in fact verify the G-forces that we were experiencing during both the hypergravity and microgravity portions. In terms of what didn't work, starting off with our electrical components, unfortunately, again, our motor failure from just the repeated use and over voltage application throughout testing made us unable to demonstrate the in-flight limit switch use, which would have indicated the linear motion of the robot both back and forth. We also experienced camera glitching due to the exceeding bandwidth limits on the computer in which was utilized in flight. For our electroadhesive pads, we did experience electrode breakage during some of the flights earlier than we had expected, as well as lamination issues during our post-flight analysis. In terms of data collection, there were some collection software issues during our second flight as well as our third. In terms of future work, starting off with results processing, although a lot of the data that we did collect did not go to plan, we are planning to continue exploring alternative quantitative processing, in which could allow us to get a better idea on what we were able to see during the flights. In terms of our robotic system, we plan on working towards hardware upgrades for improved performance. For the electroadhesive pads, we plan to improve manufacturing methods in terms of the lamination, as well as exploring other materials for the longevity of the pads. And then for testing, automating the ground testing procedures to be a little bit more consistent in terms of just a counter or applied mass. So one of the major components for our project throughout the CAN-RGX experiments was definitely outreach. And as McKenna mentioned earlier, Mission Spacewalker is a student group here at the University of Alberta. However, it was originally brought together just because of the call for proposals for the CAN-RGX experiment, and now we are continuing our research initiatives here at the University of Alberta, continuing to be a platform for students as early as high school to get involved in space exploration and research and development earlier on into their careers. So just as a quick overview of some of our notable accomplishments and achievements throughout this experience, we were awarded the SEDS-Canada CAN-RGX Outreach Award for the work in which we did over the course of the project itself. We also had the honor to share some of our learnings in a publication in the IEEE Potentials magazine in earlier 2023. We also had the opportunity to participate and present at numerous different conferences, including the Canadian Space Conference put on by SEDS Canada, as well as Nano Canada 2022 and Apaga Nexus 2022. And in terms of community, we had the privilege of also collaborating with the TELUS World of Science, the Edmonton Public Schools to put on presentations for students, as well as collaborate with WISES here at the University of Alberta to participate in both the SET and Choices conference. Throughout our experience with outreach, we have been able to inspire over 1,500 students across Alberta, which is a mission we continue to hope to grow to and contribute to for much longer than just our campaign and the projects that we are currently working on. And that brings us to the end of our presentation. Thank you so much, SEDS, for having us and for the opportunity to both participate in the research itself, but also grow our community and grow our space community here at the University of Alberta.
What an amazing presentation. Thank you so much. I found it very informative and visually appealing. So thank you guys for putting something together. I guess we'll give it another moment for people to throw their questions in. There's always a bit of a delay to the actual YouTube stream, but maybe I can ask you a question in the meantime. Given you guys have had so many great outreach activities and so much success with like conferences and publications, is there a specific one of these activities that you guys particularly enjoyed and that you're going to be doing again in the future? Like, was it going to the conferences, doing the outreach events? All of the above is an okay answer.
I think this answer could definitely differ between me and McKenna, so I think it'll be good for both of us to share. I think for me, it's definitely been the community outreach that we've had. I think going out to the schools, collaborating with the Tell Us World of Science, you get to interact with so many different students and so many different stages of kind of their educational career, whether that's as young as kindergarten or high school. And I think that those specific instances are great to really hear about, you know, people's passions and the type of inspiration that they get from actually coming to these events. So definitely the community outreach.
I guess for me, Jana talked about the community outreach, so I'll talk more internally to our team. The one thing that was really awesome that I've noticed is the growth of our team members, even through the campaign. We had people step up, like now we have Emma and Allison, our leads for the CAN-RGX project, and it was really cool to see their growth through the project. And then we had like a first year like Krista, and now she's participating in the Stratospheric balloon competition. So seeing the growth of our members and how they kind of create their own vision of space through Mission Spacewalker is probably one of the coolest outreach things that we've done.
Cool. That's really great to hear. I guess a follow-up question on that, and then we also have another one from the chat as well. But it seems to be that your team is predominantly composed of like women or gender diverse individuals. Is that something that you guys have kind of fostered on purpose? And have there been advantages to that? Like, it seems like people really are able to find a lot of like growth in your group. And do you think it's because of that?
I guess I'll take this first and then I'll also pass it to Jana. It was kind of not super intentional at the beginning, but it just so happened because when I ended up founding the team, the friends that I asked were female, and then we kind of just went with it. And the people we recruited, it was really cool because in my even in my aerodynamics class last semester, I was one girl out of like a class of 60. So it was really cool to start like pulling the females in STEM or the women in STEM that I didn't know before. And it kind of just created this really awesome program. And then when Jana came in as the co-president and she helped write our constitution, she really pushed for equity and the importance of like EEDI. And it even went as far as like the United Nations. So we went and presented at a United Nations Space for Women conference. And I think it is really important to focus on equity, especially in the space industry, because there is a discrepancy between women and gender diverse people in the actual industry in technical roles. But I'll pass it to Jana for her input.
I definitely agree with McKenna's sentiments in terms of the importance of EDI. I do think that the atmosphere itself of the team, I think, is definitely one of a kind, and it does kind of promote more people to come out and feel a little bit more comfortable participating in more technical work where maybe they're not as comfortable doing it in other clubs. So I definitely think there is a little bit of play there. So, but other than that, I think McKenna really summed up what I wanted to say.
Awesome. Thank you both for elaborating on that. That makes loads of sense. Another question we have is, what was it like flying 30 parabolas? Did you feel sick, or was it fun like a roller coaster?
I would say Jana and I also have different experiences, but this is the same for everyone. Experiences in microgravity kind of depend on the person. For me, it was really fun. It felt like I was flying a little bit. And 30, I didn't really get super sick. I also took a gravel beforehand, so that might have played a role. And honestly, it's just fun. I found that the second flight, though, your body gets used to it. I think the first flight, you're like full of nerves, and that kind of helps you get sick a little sooner. But by the second flight, you're kind of accustomed, and it's honestly just a ride. It doesn't actually feel the same as a roller coaster, in my opinion. One of the project managers for CAN-RGX says that hypergravity, or the 2G portion, is like the universe giving you a hug. And when he told me that, that's kind of what I envisioned in hypergravity. And it was really cool, actually. And then the microgravity just kind of feels like you're flying. But Jana, do you want to share your experience?
Yeah, for sure. So out of the 31 parabolas, I actually got to fly in 7 of them. So in terms of how it felt, I didn't necessarily feel sick. I definitely did not perceive it the same way as McKenna did, though. For I think 6 out of 7 of those parabolas, my brain had just convinced itself that we were upside down. So I was completely perceiving everything upside down. And I was like, oh, this isn't that bad. And then I realized that I was actually floating, and definitely not upside down. So that was kind of my experience, but it's definitely different for everyone.
Cool. That's funny though. These are definitely pretty unique experiences. I have Alina, one of our previous project chairs and participant in CAN-RGX, chiming in saying that that's a similar experience. I guess you guys mentioned that you're continuing on doing another SEDS project, CAN-RGX. We haven't mentioned that one at all. One, I'm guessing you're doing that because you generally had a pretty good experience with SEDS projects, which I hope you can elaborate on. And 2, can you tell us what CAN-RGX is and what your project for that is?
Do you want to take this one, McKenna? Or should I?
Go for it. You're doing a lot for leading it. So.
Awesome. So I think, so starting off with why. So definitely had a good experience with the CAN-RGX experience. It really does give you a different type of opportunity to apply all the knowledge that you're learning, for me personally in engineering, but others in science. So I think that it's definitely been a great opportunity, and it's something I'm so thankful for getting to experience, especially so early on in my degree when I was in my 3rd year, for CAN-RGX. But in terms of CAN-ARX, CAN-ARX is a Canadian analog research expedition, and essentially it acts as a platform for students to participate in a full design cycle similar to CAN-SBX and CAN-RGX, but in the context of an analog or a field campaign. So for this year, CAN-ARX is collaborating with the Living Lab Charlevoix in Quebec, which is going to be great. We are working on, Mission Spacewalker is working on a project exploring kind of a multitude of different things. So it's quite a multifaceted experiment. To kind of combine everything, we're looking at developing a modular and dual sensor that allows us to investigate atmospheric content as well as albedo during our field campaign. And the goal of this sensor itself is to be low cost and, again, open source where others can replicate it if they're interested. Another portion is the development of a turbine that is portable, in which we'll be able to actually take around the field campaign and hopefully power some of our supplies throughout the expedition itself. And then the next one is human factors. So being able to actually look at kind of the health side and the human side of the field campaign itself. And overall, everything comes together into developing a database where we'll be able to take all the data that we've collected on this field campaign and summarize it into something that is digestible to not only researchers, but also community members and the general public.
And I guess I'll just add a really important part of this project is we're doing the analog in Quebec, but then we're also using the technology that we're making to further develop an analog. It's a citizen research platform on the Athabasca Glacier. It's in partnership with Rockaboo Mountain Adventures and Parks Canada. And this is really cool because any citizen can register and then do research on the glacier. And hopefully our sensors will be deployed there as well as our wind turbines. So that's also another aspect. And then to your question about SEDS, SEDS is incredible. I pretty much do every project I can just because I think it's so cool. And one of the things actually that happened last year during the campaign was I actually got a job from the CAN-RGX campaign, and I got to work at the NRC next to the Falcon 20 and all of the helicopters. So if anyone's considering a project, I definitely think you should, because it not only develops your skills, but opens doors that you might not have seen possible before. Like Abrar said, touring the CSA, that's an opportunity that you can get through these projects.
Those sound like such unique opportunities. That's fantastic. That's awesome. And I'm glad you have had such a good experience with SEDS. I also think that sounds like a really, really cool CAN-RGX project. So hopefully we'll continue to stay posted on that. Maybe now we only have a couple more minutes. I'll just toss out a few general questions to either one of Mission Spacewalker or Stratoneers. You can answer them if you want, or you can just pass on them. But any advice for incoming SEDS teams? I know you guys talked about kind of your highs and lows, but if you had to just give like a couple lines of advice, what would they be? I'll toss it over to Abrar first, just because we haven't heard you speak in a while.
Advice wise, I would say plan early. Like if you're already in the project, interested in the project, plan early. It saves a lot of time. Also, always feel free to reach out to SEDS because these are professionals who have been doing this for a long time. They may know about stuff that you don't know that you don't know. That helps a lot. Like, for example, there's like a lot of concern that people would be so lost in this, especially in my first year doing this. And then reaching out helped a lot instead of, we did a mistake where we were like, we wasted a whole month trying to figure it out ourselves. And then when we failed to do the mounting design, then we reached out and they were like, oh, that's just simple. That's like, we provide that. And so that's an example of why you should always reach out to SEDS. It's been an amazing experience. But yeah, I would say planning early and reaching out to SEDS saves you a lot of time and effort.
That makes sense, and that's good to hear. I'll toss it over to Mission Spacewalker now.
I think if I had any advice for anyone who was interested in doing a project, I'd say just go for it. I know, speaking from my experience, I was definitely a little bit more, I guess, like risk averse. Like I definitely wasn't one to jump into a project, but I think that the entire experience is a learning one, and you have so much support along the way, both from the SMEs as well as the SEDS team. And I think that if you do have an interest, definitely reach out and submit a proposal and see where it goes, for sure.
Cool, that's awesome. Great advice. I guess just one last question building on all of this. Are there any particularly good resources you all have had to kind of carry out your projects? They seem pretty advanced engineering projects, at least to someone like me. And I imagine other people might be intimidated by the level of skills that are needed to execute something like that. Were you guys intimidated at first? And did your classes prepare you enough? Did you use other resources? I think SEDS, the CSA and stuff was mentioned, but just touch on that a little bit more.
I can start off on that one. Yes, definitely intimidating. When I first started, I was just designing the payload, like just the external structure. I was the mechanical manufacturing lead over there, and all that aspect seemed way too complicated. And I was like, first year, I was like, I just need to do this. I don't really need to involve myself. But that's the thing. I feel like your classes definitely help. However, I think a more beneficial factor is your teammates. Always like have an ear out of what your teammates are contributing to. And like I said, the factor of not knowing what you don't know, teamwork and their perspective, design perspective, their innovation, their curiosity, their creativity helps you a ton. It's like I said, everyone who's going into this project have to be confident, but you also have to have the idea that there are a lot of stuff that you don't know, and collaboration and cooperation just solves that. It's a problem, but it's also not a problem if you act on it properly. And yeah, that's what I would say.
Thanks so much for elaborating on all of that. Mission Spacewalker, do you have anything to chime in? I think Avar's presentation, Avar's answer was pretty through and through, so if you don't, that's okay.
I guess I'll add, our advisors were really helpful, especially Dr. Samioto. He let us make electroadhesive pads in his lab, and then Rick was the technician, the electrician, who helped us a lot. And then we also had Chantel from the CSA who helped us. So I think advisors are so important, and I would highly recommend that any team tries to get someone who's interested and kind of specialized in their field to get their advice throughout your project, and also rely on your members. For us, during the campaign, one of our cameras failed, and it was the day before our flight, and so we had to come together and find a solution. We ended up running around Calgary, found like a little cheap webcam and resoldered it with Sharuk, who was one of the SMEs on NRC, his help, which can be kind of stressful, but when you think of it, everyone who knows me knows that I say everything is astronaut training. If you think that way, then even the hard things prepare you for the future. So whether that's trying to find an advisor or working with your team, your mission crew, I think the resources really come from people and the people that you know.
These are both such wholesome answers. Thank you guys so much for the wholesome and useful answers you provided today. And thanks for the presentations. I thought they were fantastic. It's really lovely as SEDS that we can show off such successful teams to come out of our projects, like the both of you guys have led. I'll also thank everyone for tuning in to the live Zoom today. And those of you that asked questions, particularly, thank you. We'll be signing off, but if you have any questions, feel free to scroll around on the SEDS website. We accept applications for these projects every year for the foreseeable future, and we'd love to have you join and maybe have as much success as these two teams did. So thank you all again.